Hi, so today I'm going to be going over my Moore design. This was the one that actually won out in the Moore versus Mealy criteria where I had to weigh certain categories and determine which one was the best. So over here, this is where I started. This is my legend. I had a state key stating that a bubble here represents a certain state with the name and the state number. And this is the input that defines the transition from state to state. Over here, this represents what each of these variables mean. So C is the charge on, V is an over temperature error, S is a start charging input, and T indicates that the temperature has been exceeded, or the maximum temperature has been exceeded. Now over here, this is my state diagram. So this is my reset state, and when you're in a reset state, you want to keep the relevant state numbers as both zeros. So this indicates that the charge is off, and this indicates that the over temperature state has not been reached. Now over here, I made an assumption that whenever you're in S0, if you put in an input where the charge is 0, but there's an over temperature or there isn't an over temperature, it's going to stay in S0 regardless of what this is. Now if you want to transition to the charging state, which is this one, you're going to put in a 1, 0, and if you're in the charging state, if you put a 1, 0, then it's going to stay in the charging state, but if you put in a 0, 0, it's going to transition back to the reset state. And this applies to S2 and S3 as well. If you're in S2 or S3 and you put in a 0, 0 for the charge on and the temperature input, it's going to go back to S0 for both this state and this state. Otherwise, if you're in S0 and you have a start charging and an over temperature, it's going to jump directly to S2. And these states over here indicate that an over temperature condition has been reached. And if this exceeds 3 over temperatures in 3 clock cycles, with 3 consecutive clock cycles, then it's going to be in a state of lockdown. And when you're in a state of lockdown, then no matter what you put in for the inputs, it's going to stay in lockdown unless you reset. So this is my state transition table. This basically just indicates what the next state is going to be given a certain input. And these are the outputs relevant to each state. This is my state assignment table indicating what each state represents in terms of binary numbers. And this is my new state transition table with the numbers put in place for the state names. And these are all the don't cares for the values of the states that can't exist. So these are states S0 through S4, and all these other states are just states that aren't possible with a given model. Now this is my truth table. This column right here represents all of the possible values for S and T, QT, Q1, Q0, just all the different possible combinations there. And then these are the next states given a certain input with a certain state. And then these are the outputs relevant to each of those next states. Then once I had that information, I extracted 3 5-term Karnaugh maps, which have 2 4-term Karnaugh maps to represent basically just what's happening. And then from those, I extracted these Boolean expressions. And then over here, I have the outputs and how those outputs apply to whatever the current state is. So once I had all of this information, then I went over into Quartus and created this circuit design right here. And then as you can see, the design is going to compile successfully. All right, so the design has compiled. That is the Moore design right here. So if I create a new waveform diagram to represent this and just import all of the nodes, right here you can see that we have S, T, the clock, a reset, and then output C and B. So let's say I made a certain clock happen like this, where these are the different cycles, and just like, let's zoom in a little bit here. All right. So if I make S equal to 1, then on this negative edge right here, the output C, representing the charging, is going to equal 1 up until the next negative clock cycle. And then it's going to go back to 0 because S is equal to 0. So let's run that real quick. Make sure that behaves as expected. Yeah, so as you can see, hold on. Okay, so S is equal to 1 right here, T is equal to 0, and then once you hit this first negative edge right here, the value for the charging is going to equal 1, but then once it hits this clock cycle, it's going to notice that S is now equal to 0, so it's going to set the value for charging equal to 0, meaning that we're back in state 0. Now if I go back, let's say what can I do? Let's say afterwards I have an certain over temperature condition, so make that S1, then make that S1, then make that S1. Okay. All right, so now if I run the simulation, this basically represents that it's charging, and then you have 3 different over temperature conditions. So if I run it, just wait a second for it to compile. Okay, if I run it, you can see that it is charging over here, and this is fine because there haven't been any over temperature conditions, and then once S is equal to 0, then it sets back to a state of not charging. But as soon as you have the first over temperature condition, then it goes to 0, and then as soon as you have 3 consecutive over temperature conditions, which are right here, then the state of lockdown goes to 1, and it stays in 1 unless there's a reset. So hopefully that is a sufficient representation of my Moore model design. Thank you for your time.